So we do have homework.
So you we'll have any homework that's due for Friday, but you will have homework that's due after break. Yeah.
Okay.
Yep. Yep, I did that on purpose. Yeah. So, so the assignment slide, we're like 2 or 3 slides before that. Puts us where I want to be. So, all right. So we're going to talk about chemical equilibria. So, and we've been like when we do an elementary step, it says fast equilibrium. That's a chemical equilibrium. You know it's a chemical equilibrium because it has an arrow going to the left and the arrow going from the right back to the left. Wait, going from the left to the right and the right to the left. Two-way arrow. Okay. So the word dynamic is kind of what it means. It's always changing. So basically, reactants are going to form products, and products are going to form reactants. Now, at equilibrium, it looks steady state because at equilibrium, your concentration of your reactants and products is set. But they're trading places, okay? And we use this actually in our calculations for our mechanisms. The fact that if it's at equilibrium, then the rate in the forward direction is equal to the rate in the reverse direction, if it's at equilibrium. Okay. So we're looking at this reaction, carbon monoxide and hydrogen gas goes to form methanol, and it's in equilibrium, okay? And we have like 3 different scenarios here. Now, the way you read this, of course, along the x-axis is time. Pull my little pointer here. So we have time is increasing. Let's see, it's kind of color-coded, so our 2 reactants are the colored, and then the black one is the product. So does this make sense that basically you're starting with 0 product, and then after some time, and actually it's neat because the gray starts where, can you see after the gray that the concentration of everything's the same. So after the gray, chemical equilibrium has been reached. Before the gray, of course, what you need to do is kind of settle into some equilibrium concentrations. What does that mean? It means both of the reactants will decrease in their molar concentration along the y-axis, and your product will increase. Okay, well, we could look at the same chemical reaction. Okay, this is different. Notice in this scenario, we basically have only the product starting out, and we have none of the reactants. It can happen. So basically, the product is going to decompose back into the carbon monoxide and the hydrogen gas. Okay, and so you see but we still call these reactants and these products. And you see the molar concentration of the product decreasing, the molar concentration of the reactants increasing. Okay, and we reach new equilibrium amounts. So one more scenario, where this is kind of fun. We basically have a smidgen of everything. The units along the y-axis are moles per liter. So, or would they be, I don't know, they might be partial pressures. But anyway, we have a little bit of everything, and notice how it splits. We end up forming more of our reactants, okay? And of course, some of your product is going away. Now, we haven't talked about enough for you guys to know, first off, which way it's going to go. This one's most interesting, I think. By the end of Unit 3, you guys will know, based upon more information about this equilibrium, you guys will know that it's going to split this way. Okay, and reactants are going to increase and the products going to decrease. We'll talk about that. But these are all 3 different scenarios, same chemical equilibrium. So we talked about rate law expressions, and I'm a little apologetic at this point, but rate law expressions are hot on your minds, hopefully, for tomorrow's test. Equilibrium constant expressions, then, are again mathematical, and they have another K. Okay. But they link mathematically the molar concentrations, not just of the reactants, but the molar concentrations of the reactants and the products at equilibrium. So remember how we had like a generic rate law expression? Okay, so this is our generic equilibrium constant expression. Okay, so it looks like this, where actually we have two reactants in equilibrium with two products. We'll use capital letters for what the species is. We'll use lowercase letters for the stoichiometric coefficients. Okay. Then we can come up with our kind of out-of-the-box rate law expression. Sorry, oh, darn it. Out-of-the-box equilibrium constant expression, direct. This is a capital C and a subscript C. Darn it, are you serious? Capital K with a subscript C. Okay, this is our equilibrium constant, that we will be kind of substituting different subscripts here, is equal to the molar concentration, and you always put the products on top, the molar concentration of the products. Now you get to use their stoichiometric coefficients. These are not reaction orders. These are literally just raise it to that power. Okay, D raised to its stoichiometric coefficient, the products in the top, in the denominator, the reactants. Stoichiometric coefficient, stoichiometric coefficient. That's it. Yep, so like I said, I tried to say it the second time. So Kc is your equilibrium constant. And equilibrium constant, it does depend upon temperature. And then anytime you see something in brackets, that's molar concentration of. So, and it's the products always in the numerator. One of the things that, and I don't know if it's just me, but I struggle with, if it's something's at equilibrium, you're like, well, who's to say these are the reactants? And who's to say these are the products? Well, whoever wrote it down is to say. So kind of from left to right, we still call them reactants products.
So had they written it down CD, first, then, okay. So it just depends on how it's written.
It depends on how it's written, but thinking of it this way, can you see where actually if you swing it around and write it the other way, your expression's going to basically be the inverse.
Right.
Yeah. So if somebody gives you because there are Kc values out there. There's equilibrium constants out there. When they give you that, they have to actually associate it with an equilibrium in particular order. Okay, so your K or Kc, and you'll kind of see me sometimes, I'll kind of drop the C, but this just means molar concentration. So your equilibrium constant, molar concentration, it's got to be constant as long as your temperature is the same. So this is, and we'll get more into this, but just a little bit ago, we looked at 3 different scenarios for that one equilibrium. If you look in the gray area where the equilibrium concentrations are, those actually mathematically all have to be the same raised to the stoichiometric coefficient. So I think that's neat.
Sorry, can you say that?
Yeah, the figure of this one right here. So these gray amounts, okay, if you plug them into an equilibrium constant expression, mathematically those final amounts will all be the same value, raised to the stoichiometric coefficient. Okay. Yeah, it's kind of neat, I think. So here's another one for you. So remember I said that if something's in equilibrium, then by golly, if you take a snapshot of the concentration of your reactants and the concentration of products, if it's at equilibrium, that's not going to change as long as you hold the temperature. Now, it is dynamic, so you kind of have some swapping back and forth, but the molar concentrations are constant. This talks about, and remember when we looked at solubility, which is another type of equilibrium. It's not chemical, but it's physical. When we talk about solubility, we talk about Le Chatelier's principle, where you could stress a system in equilibrium. We're going to be doing that, and when you stress a system, then it's no longer the rate of the forward direction. The rate of the reaction in the forward direction is not equal to the rate of the reaction in the reverse direction. So if you stress it, Le Chatelier's principle, then it's not at equilibrium, and your concentrations are not constant. All right. So, been focusing a lot on units. So, your rate law constants have specific units, okay? As it turns out, this equilibrium constant, Kc, is unitless. And you might see, well, oh my gosh, how could that be? Because it seems like it should be some sort of crazy moles per liter, right? And I'll show you how this works. And you can, if I don't convince you, you can read in your textbook how it works. But basically, if we think of those molar concentrations as being divided by this standard amount, which is the same species, 1 mole per liter. It looks like this. Okay, so for this example, we have 2 reactants, 1 product. Of course, in the numerator is the product, methanol, raised to its stoichiometric coefficient, which is 1. We go ahead and introduce, to standardize it, this 1 mole per liter of that species. The interesting thing is then, the moles per liter introduced by the molarity will cancel with the moles per liter introduced by the 1 mole per 1 liter, and your units cancel, but you haven't changed the number at all. We could do the same thing down here. Of course, stoichiometric coefficient in front of H2 is 2. So in the equilibrium constant expression, we're going to raise that molar concentration to the 2nd power. Okay? And here again, we can remove the units by just introducing a standard 1 mole H2 per liter of friction. And the moles per liter cancel, and we're left with that unitless. So again, I don't really...
So those on the left those are standard, like
that's
known, that's not going to...
That is, it's a way to standardize the whole problem. And that's what's kind of happening behind the scenes for all of these problems.
So that's like what you're assuming?
Right.
For your problem.
Yes, that's what we're assuming. Exactly. And so what you'll see actually is the equilibrium constant expression for this equilibrium written just like this. That's how you'll see it. And again, what's happening behind the scenes is basically the units are being removed. Okay. So K, units of K, Kc will be unitless.
Sorry, so that one is the same as that one?
This one down here is how you'll see it written.
But it means the one up above?
Yeah. Yep.
Okay.
This is kind of implied.
Okay.
Because, and in this scenario, your units cancel.
Okay.
Yep. And so all you carry along, if your units cancel, in applying the standardization technique, if your units cancel, all you're carrying along is the number. So we carry the numbers of the molarity of your methanol, the molarity of your carbon monoxide, and the molarity of your H2. And that, the whole beauty of this, or all this means, is that's unitless, which we're happy about. Okay. So, a little bit ago, well, I guess this won't work, but we'll go back to that. So when somebody gives you an equilibrium constant, if it's pretty big, check this out. And to me, I don't memorize things very well, so I always have to think through it. So if this is big, then to me what's big is this up here. And what's in our numerator are our products. So a big equilibrium constant means that it actually favors, you have more products at equilibrium significantly than you have reactants. That's how I think of it. Usually works pretty good. If this is small, if your equilibrium constant is small, then that means that you basically have a big number down here and a small number up there. If you have a big number down here, what's that? Well, that are your reactants. So, and if it's in between, then kind of at equilibrium, you kind of have a nice mix and match of reactants and products. Similar amounts. Okay. So these are some equilibrium constants over here on the right. Check out the first one, 4.1 times 10 to the 83rd. There you go. Really favors the products, okay? The next one, 1.9 times 10 to the negative 23rd, okay? Really favors the reactants. This number is really big, okay? The next one is kind of in between, and then we have another one that also favors the reactants.
What's the difference between the C and the P?
Oh,
Is that just another way of?
well, we'll be talking about this. This one means molar concentrations, and this one actually means partial pressures. Yep, just different ways to express the equilibrium amounts in molar concentrations or partial pressures. Very good. Okay, so let's write a couple. They're not bad. So again, it's reactants over products, and in this case, your stoichiometric coefficients become the powers that you raise it to. So in this case, we'd say Kc is equal to the molar concentration of O3 raised to the second power divided by the molar concentration of O2 raised to the third power. And then in the next one, again, it's always products divided by reactants. So Kc would be equal to molar concentration of NO2 raised to the fourth power times the molar concentration of H2O raised to the sixth power divided by the molar concentration of NH3 raised to the fourth power times the molar concentration of O2 raised to the seventh power. You guys must have already had those, did you? Okay, there's my blank paper. So that's how far I wanted to get. So, but like I said, after I give you back your test and maybe hit some highlights of the test, then I will plan on finishing this whole part, which means 2 assignment sites. That's not bad. And there's a review session now.